Welcome friends to this third lecture of week 12 of soil science and technology, and in this lecture we will try to cover several quantitative models for digital soil mapping, and let us start with the decision tree. So, in the last lecture we have covered this linear regression, which is a global model where there is a single predictive formula holding over the entire data space. However, sometimes the soil data are non-linearly related. So, we may be interested to explain or maybe model them through non-linear methods. So, one of these model structure, nonlinear model structure, is called the classification regression trees. And this classification regression tree or CART are a non-parametric decision tree learning techniques that produces either classification or regression trees. And regression trees, we use the term regression tree when our target is numeric, when, or in other words it is a continuous variable, and we use the classification trees when we use to model a categorical variable. Now, categorical variable are not continuous variable. Categorical variable meaning any name nominal variable are considered as categorical variable. So, decision trees are basically either regression or classification are formed by a collection of rule based or variables in the modeling data set. So, remember this classification tree or regression tree is basically a rule based algorithm when the rule based on variable values are selected to get the base split to differentiate observation based on the dependent variable. And once a rule is selected and splits a node into two, the same process is applied to each subsequent node, and the splitting stops when CART detects no further gain can be made or some preset stopping rules are met. Alternatively, the data are split as much as possible and then tree is later pruned. So, here let me explain. So, here you can see this is a decision tree or classification regression tree. Here we are trying to we are trying to model, for example, say for a particular soil property based on, or soil organic carbon based on several soil covariates. For example, elevation, then topographic wetness index, then Landsat band 3 reflectance values, and then radiometric potassium from gamma radiation, and so on and so forth. So, basically our target in this case is soil organic carbon, and we want to differentiate or want to divide or want to make a rule so that we can predict the soil organic carbon based on these rules. So, in the first step we will select which among them, we have 4 here, 4 to 5 different predictor variables. So, we will select the best split and or best variable values to get the base split, so that it can give you the maximum separation between the observation based on the dependent variable. In our case it is organic carbon. So, here it might, we have selected this elevation value of 238.7 because it gives the maximum clear separation between two groups of data. And once this rule is selected and split is node and we split the data into two nodes, into two parts, the same process is applied to the subsequent node. So, in the subsequent node, so this is the first node and this is a subsequent node, again we select which among these 5 or 4 different variables are important and what are their values. So, we have seen that in the subsequent node this TW value of 22.4 is the most important splitting criteria, which can split the data into 2 more groups, and so on so forth. You can see this process grows on. So, that is why we call it recursive splitting process. And when the splitting stops, the splitting stops when CART detects no further gain can be made or some preset stopping rules. We will discuss these details, what are these gains and what are these stopping rules. Alternatively, the data are split as much as possible and then tree is later pruned. So, other way we will allow this tree to grow continuously, and ultimately once these trees are grown, these are individual leaves and terminal nodes. These terminal nodes will go for pruning. You know, the cutting of the branches is called pruning. So, similarly here, if we cut these branches, cut these individual branches, obviously these will be further clubbed together. So, this will call pruning. We will discuss this later on. So, each branch of the tree ends in a terminal node and each observation falls into exactly one terminal. So, you can see based on this rule based thing, you can predict, you can segregate each of the observation into each of these, any of this rule. For example, any observation can come in this rule where, which is defined by elevation values of less than 238.7 and TWA value of 22.4. So, this is the rule for classifying a particular observation into this terminal node. So, you can see each of the observation can be generalized in terms of these rule based thing. So, let us see a good example. I have found this example, so I want to show you so that it will be very much easy to understand. So, let us see, we have to classify or predict an outcome based on a set of predictors and the output is a set of rules. So, example here, our goal is to classify record whether a person will accept a credit card offer or will not accept a credit card offer. I am just giving an example so that it will be easier for you to understand what is going on in this classification regression tree. So, our goal is to classify a record as either he will accept credit card offer or he will not accept a credit card offer. So, the rule might be if income is greater than 92.5 and education is less than 1.5 and family is less than equal to 2.5, then class equal to 0, that is non accepted. So, they will not accept. So, this is the individual rule we generate using this classification regression tree. So, also called card decision trees or just trees. So, rules are represented by this tree diagram as we have seen in the last slide. So, as you can see here, we have classified all the observation based on some rules. So, again here as I have told you, if the income is greater less than this 92.5, then there are 417 observation, and then based on that, if the education is greater than 1.5 some index, then it will further classify into 157 observation and 260 observation and so on so forth. Ultimately, you can see ultimately the end product is either it will accept or reject. Reject is 0 and accept is 1. So, this is how we can differentiate any value. So, you can see all the observations are differentiated into these individual rules. So, let us see how we create this thing. So, key ideas in this case is recursive partitioning, and recursive partitioning, as you have known, that is repeatedly split the records into two parts so as to achieve maximum homogeneity within the new parts. So, the splitting criteria says that we will select that particular value of the variable as a splitting node, where we will get the two split, and in this two split the variables will be maximum we'll see maximum homogeneity within these variables within this observation within a single split. Again, we will select the splitting node or the particular variable and their respective value in the splitting node in such a fashion so that we can differentiate the groups of observation, and in these individual outcome groups, those observations in these groups will be maximally homogeneous. So, once you get that, another term is pruning, which is simplify the tree by pruning peripheral branches to avoid overfitting. We'll discuss that later on. So, let us see how we do this recursive partitioning steps. So, we have to pick up one predictor variable, say it is xi, and pick up a value xi, say pick up a value of xi, say si, that divides the training data into two not necessarily equal portions. Then we have to measure how pure or homogeneous each of the resulting portions are. Pure means containing records of mostly one class, An algorithm tries to different values of xi and si to maximize purity of the initial series. So, there is this algorithm tries several combination of xi and si to find the best split criteria. After you get the maximum purity split, repeat the process for a second split and so on. So, that is why the tree grows on, and you can see why we call it a tree, because a tree has several branches. So, as you can see, these classification regression trees are also having several branches and then sub branches and so on and so forth, and then these branches again split. Let us see our example. Our goal here, I am just taking one example from which I have seen lately, so that it will be easier for you to understand. Let us see, our goal is to classify 24 households as owning or not owning riding mowers. So, our predictors here is income and lot size. So, you can see these are 24 observations. The first column shows that the first column is basically the income, and the second column is the lot size, and finally third column is the ownership, either it is the own owner or either owner of that lawnmower or non-owner. So, based on that we have to predict using a classification and regression, and here our target will be these two classes, owner and non-owner. So, how to split? So, order record according to the one variable, say lot size, and then let us find the midpoint between successive variables. For example, first midpoint is 14.4, which is halfway between 14 and 14.8, then divide the records into these two, those with the lot size, for example, greater than 14.4 and those less than 14.4. And after evaluating that split, try the next one, which is 15.4, which is halfway between 14.8 and 16. So, you can see we are trying different combination of values to find out the maximum to find out the best split, which will give us the outputs which will be homogeneous among themselves. So, let us examine all possible ways in which categories can be split. In case of categorical variables, let us see categories A, B, C can be split in three ways, either A and BC, then B and AC, and C and AC. So, with many categories the number of split becomes obviously huge. So, let us see in our case, in case of in this more example, the first split, in our case the lot size is 19,000. So, our first splitting criteria is the lot size. So, you can see we are dividing the whole space into two groups. These black dots are owner and the other dot, the solid dots are owner and the hollow dots are non-owner. So, you can see the maximum homogeneity between these two split within these individual split. The next step will split based on the income value of $84,000. So, you can see there are three more split, there are two splits again within this split, there are two more splits, and after all the split you will get this individual split, the final results. So, this within these individual blocks or individual areas, the observations are homogeneous or maximum homogeneous. So, this is how these rules are basically formed. Another important term is Gini index, and Gini index for a rectangular A containing m records can be calculated by using this formula, where P is the proportion of cases in rectangle A that belong to this class K, and IA is 0 when all classes belong to the same class, and maximum values when all classes are equally represented, where 0.50 in case of binary case. So, based on this Gini index criteria, we select the best split criteria. Again, this Gini index for rectangular A containing m records is calculated by this formula, where P is the proportion of case in rectangular A that belongs to class A, where IA equal to 0 when all classes belong to the same class, and maximum values when all classes are equally represented. Another important term is entropy. and entropy can be calculated by using this formula, where P is the proportion of cases out of M in rectangular A that belongs to class K, and entropy ranges between 0, which is representing most pure, and log to M, where equal representation of the all classes. So, what is impurity and recursive partitioning? Obviously, we have to obtain overall impurity measures, weighted average of individual rectangles. At each successive stage, we have to compare this measure across all possible split in all variables. So, we told you that for each step, we are selecting the best combination of variable as well as its value like xi and si, and these variable and their value combination is selected by measuring the overall impurity measures. So, we have to choose the split that reduces the impurity the most and choose the split point become nodes of the tree. So, in the first split, obviously this is the tree, obviously we are selecting it based on the lot size, and we are selecting 12 observations, and tree after the 3 splits you can see here looks like this, and the tree structure obviously split point become nodes on the tree, circle with split values in the center. If you see the split points, these are the circles, these are the split individual split points from which further split is occurred. So, split points become nodes of the tree, and from these nodes further split occurs, and rectangle represents the leaves. Here the rectangle leaves, this rectangle actually denotes the individual leaves, and these leaves terminal points no further split classification value noted. So, basically here in this terminal, this is called the terminal node or leaf, and from here there will be no further division. So, here this branch stops. So, this is an example of how this tree grows, and number of lines between nodes indicates the number of cases. Obviously, you can see here there the number of, here the 3, that means the number of cases, and 9 here is the number of cases obviously. So, if the lot size, read down the tree to derived rule, if the lot size is less than 19 and if income is 84.75, then class is owner, and so on so forth. Determining the leaf node level, obviously each leaf node level is determined by voting of the record within it and by the cutoff values, and records with each leaf node are formed by training data, and default cutoff values is 0.5 means the leaf node level is the majority class, and cutoff of 0.75 requires majority of 75% or more 1 records in the leaf to be labeled as one node. So, after all the splits you can see these circles are the splitting nodes, and is the splitting nodes you see we have selected a particular variable and the particular value of that variable which gives the lowest impurity, and then and ultimately the tree grows, and these are the branches, and ultimately you see these rectangular boxes are the terminal nodes from where there will be no further splitting, and ultimately you will see that there is ultimately we are specifying whether they are owner or non-owner, which is our target classes. So, what is the overfitting problem? Obviously, remember that if you continue go on and create the trees and create these branches and all these things, ultimately a time will come that you will perfectly fit all the observation, because each of the observation will have their own set of rules. So, you can create any set of rules to fit any particular observation. However, that would create overfitting. Now, what is overfitting? If any calibration model performs poor in case of new set of data or independent data set, that is called overfitting. For example, you have created a very good calibration model and you try that calibration model to predict some unknown samples and that performs miserably. So, that is called overfitting. So, natural end process of this CART or classification regression tree says that you will get 100% purity of the leaf, because you can create any rule to put any sample, or you can create any rule to define any sample, and this overfits the data, which ends up fitting noise in the data. So, overfitting leads into low predictive accuracy of the new data, as I have told you. So, past a certain points, you see the error rate for validation data sets start to increase. You can see here, as the number of splits increases up to a certain point, you can see that if you increase the number of split, a time will come that the training data error will go down and ultimately reaches 0, as you can see in this green, in this blue line. However, the problem is, as although this training data set produces very lowest error as we continuously increasing the number of split. However, you will see if we test this training model or calibration model using the unseen data or independently drawn data, their error rate will increase after a certain split. So, this is basically saying that this model is overfitted. So, we need to do some kind of treatment to reduce this overfitting, because our ultimately aim is to get a representative model which can predict reasonably the unknown or unseen data. How do you do that? Another one method is called chain method, which is older than CART method, which is using chi-squared statistical test to limit the tree growth, and the splitting stops when purity improvement is not statistically significant. The most important way for reducing this overfitting, or to remove this overfitting, is the pruning. And CART lets, first of all, in this pruning method, the CART lets tree grow to full extent, then prunes it back, that means cutting the individual branches, and when we are cutting the individual branches, obviously we are eliminating that particular rule. So, ideal is to find that point at which the validation error begins to rise, and generally successively smaller trees by pruning leaves. When we are pruning the leaves, obviously it will get, the trees will get smaller, and at each pruning stage multiple trees are possible, and use the cost complexity to choose the best tree at that stage. Obviously, we have to use the pruning across yields. A pruning process yields a set of trees of different sizes and associated error rates, and two rates of interest are there for us for while we are doing the pruning. Minimum error rate, that is, has the lowest error rate on validation data, and best pruned tree obviously shows smallest tree with one standard error of minimum error, and this adds to bonus for simplicity or parsimony. So, let us see what is the actual example of use of classification and regression tree in DSM. As you can see here, we are predicting the soil organic carbon to 0 to 5 centimeter using this classification and regression tree, and this classification regression tree you can see here, using that we are predicting, this is actually the observed versus predicted values. The problem in classification regression tree is that you can see some specified levels of predictions. So, this is a problem in case of classification regression tree. Again, this classification regression tree, you will see some specified levels of predictions, and this is a problem in classification regression tree which we generally address by another tree method. We will discuss them, and but here is an example of use of classification regression tree, or we call it finite finite predictions. So, this is an example of decision tree predicted 0.5 centimeter long log carbon stalks. So, again, this classification regression tree is a very important method, nonlinear method to generalize the to produce the nonlinear prediction of soil properties. The QBIST model, another model is QBIST model. The QBIST model is currently the very popular model structure, model structure used within the DSM community, and its popularity is due to its ability to mine nonlinear relationship in the data, but does not have the issue of finite prediction as we have seen in case of classification regression tree. And the QBIST model first partitions the data into subset within which their characteristics are similar with respect to the target variable, and the covariates, a series of rules. For example, a decision tree's structure may also be defined if requested, defines this partition, and these rules are arranged in a hierarchy. Each rule has the form either if, which basically shows if the condition is true, then we will fit a regression model, and if the condition is not true, then else we will apply the next rule. So, this is how it will fit the whole data, and ultimately based on a condition is met or not, it will create a regression in this particular ultimate terminal node. So, this is how a QBIST model works, and QBIST model is the nowadays considered as the most advanced method as far as the digital soil mapping of soil is concerned. And this is an example of QBIST produced soil organic carbon map for a particular area of Australia. And you can see this is the QBIST predicted 0.0 to 5 centimeter logarithmic carbon stocks, and this is the predicted versus observed values, and you can see there is no finite predictions problem as we have seen in case of classification regression tree. Another important aspect, another important method is random forest. And random forest is a boosted regression tree method. Remember that random forest is an ensemble learning method for classification and regression that operates by constructing multitude of decision trees at training time, which are later aggregated to give one single prediction for each observation in a data set. And for regression, the prediction is the average of the individual tree output, whereas in case of classification tree votes by majority of the correct classification model. So, what happens? We have known what is a tree in case of classification regression tree. So, in case of random forest, we create thousands and thousands of individual tree by randomly selecting the variables as well as randomly selecting the samples. And once we create these thousands and thousands of trees based on their prediction results, and once we create these thousands and thousands of trees, we call it random forest. And what is the output value? For regression, the prediction is the average of individual tree output. So, we are getting average, we are getting the individual tree output, and once we are taking the average of this individual tree output, that will be the overall output or average output of this random forest. And in case of classification, we take the majority of the votes from these individual trees. So, that is how a random forest basically operates. A random forest is more advanced method. A random forest is a widely used method in case of digital soil mapping. So, random forest forms lots of decision trees with random selection of samples and random selection of features. So, that is why it is called random forest. First of all, it is called forest because we are using thousands and thousands of trees. And it is called random because we are using random selection of samples and random selection of features for creating one particular tree. So, that is why it is called random forest, and it provides the class of dependent variable based on many trees. That is why it is called random trees, many random trees, random forest. The random forest basically assume that most of the trees can provide correct prediction or class for most part of the data, and the trees are making mistake at different places. So, based on this observation, it calculates the final output. In case of regression, it calculates the average of the output, and in case of classification, it calculates the majority of the vote. So, here you can see the example of random forest, and random forest obviously you can see this random forest predicted 0 to 5 centimeter logarithmic carbon stocks. And another beauty of random forest is based on certain criteria you can get the ranking of the important variables. For example, here in this random forest example, we used elevation, Landsat B3 band, TWI, that is topographic wetness index, Landsat B4 band, and radiometric potassium. All these 5 covariates as predictors, and you can see here they are arranged based on their certain properties like increase in mean square error and increase in node purity. So, these are arranged based on their importance. So, that is why random forest has the capability of arranging the variable based on their relative importance also. So, this is an example of random forest application for predicting the log carbons. Another important hybrid method is called regression kriging. Now, regression kriging is basically combination of both regression and kriging, and kriging is basically the best linear unbiased predictors of spatial data. We know from our geostatistical discussion that a value of a target variable at some location can be modeled as a sum of the deterministic and stochastic components. So, it is a value of a particular variable at some location can be divided into it is a deterministic part and it is a stochastic part, and obviously there are some errors. So, we know that both deterministic and stochastic components of spatial variation can be modeled separately. So, you can see, so by combining these two approaches we obtain a final output where ultimately this is the output of the stochastic deterministic component, and this is an output of the stochastic component. So, this is basically the deterministic component and this is the stochastic component. So, in the deterministic component you can see this is basically a linear regression equation, where these are basically the individual coefficient, and here this is basically you can see it is a kriging kriging output, where AMS0 is a fitted deterministic part and this is a interpolated residual, this is an interpolated residual, and this BK is estimated deterministic model coefficient. So, if we are using the linear regression model, these are the model coefficient values, and lambda is basically kriging weights determined by the spatial dependence structures of the residual, where ESI is the residual as location Z SI. So, basically you can see here we are using two components. First of all, we are trying to produce a model output based on the deterministic model. The deterministic model may be linear or non-linear, and using the residual we are interpolating the and we after calculating the residual from this model we are basically interpolating them. So, this regression kriging is basically the combination of deterministic model output and the interpolated residuals. So, this is why it is called a hybrid method. So, how this works? So, you can see this regression kriging the deterministic model essentially detrains the data, leaving behind the residuals for which we need to investigate whether there is an additional spatial structure which could be added to the regression model prediction. These residuals are the random components of the Scorpion plus E model. As we can see, if these are the field samples, these are the field samples. So, these are basically the distribution of distribution of the target variable if you sample it very densely. So, once we collect these samples, these are the field samples. Our next step in the deterministic model, this in the x axis this is a geographic space, in the y axis this is the target variable. So, basically we are detraining the data by first fixing a regression function or deterministic part. So, this dotted line is basically the regression function, and by using this regression function we are basically detraining the data. So, once we are detraining the data, this is the residual, this is the difference between the actual point and the point on the regression function or regression line. So, this residual, the next step we will basically Krige the residuals, and ultimately you see this line is basically the final estimate by regression kriging. So, it is basically the combination of kriging residuals as well as the output from deterministic regression function. So, it basically shows the schematic example of regression kriging fitting a vertical cross section with assumed distribution of an environmental variable in a horizontal space. So, I hope now this regression kriging is clear to you. So, that is why nowadays we not only rely on kriging, we also rely on different types of advanced models. Either it is a linear model, either it is a non-linear model. So, we basically combine the output them together both from kriging and deterministic model to give the most unbiased estimator of the spatial variability, and that is called the regression kriging. And these are the example of some regression kriging method. You can see the first one is QBist predicted 0.5 centimeter logarithmic carbon stock of 0 to 5 centimeter, and then these respective Krige residuals, and finally this is a regression kriging predicted 0.5 centimeter 0 to 5 centimeter log carbon stocks by combining these two output. So, guys, let us start another important thing, that is modeling and mapping of categorical variables. Remember that we have covered the continuous variables, and now another important term is categorical variables, and sometimes it is very important to model the categorical variable in case of digital soil mapping also. And remember that the special characteristics of categorical data and its prediction within the model is a class is either predicted or it is not, and for binary variables the prediction is either a yes or no, black or white, present or absent, etc. For multinomial variables, there are more than two cases, for example, either black, grey or white, etc., which could actually be an ordinal categorical classification rather than nominal, and there is no between, rather discrete entities. And important quality measures are overall accuracy, users accuracy, producers accuracy, and kappa coefficient. Let us wrap up here, and in the next lecture we will discuss these different accuracy measures and different types of categorical models which you use for digital soil mapping. Thank you.